Okay, so I'm Praneeth and I'll be talking about fast and small subspace embeddings. This is joint work with Nadia, Ken Clarkson, and my advisor David Woodruff. So what are subspace embeddings? Here we are given a arbitrary d-dimensional subspace, say in R to the n, and you want to map each vector in the subspace to an embedding of the vector. That is, you want to map x to E of x, and typically you want E of x to lie in much smaller dimension in R to the m for m much smaller than n. Okay, and a useful property to preserve is that Euclidean norm of this embedding must be very close to the Euclidean norm of the original vector we are trying to embed. So this is the condition we require of our embedding. That is, for every x in the d-dimensional subspace V, we want Euclidean norm of E of x to be within 1 plus minus epsilon of the Euclidean norm of the vector x. And ideally, we would also like this embedding to be linear. That is, E of x should be of the form f times x for a matrix f. This is useful for many applications such as streaming and so on. So we want f to be linear. And this is the analog of JL transform that we all know. JL transform tries to preserve Euclidean norm of a fixed set of n vectors. But here we want to preserve norms of every vector in a d-dimensional subspace, right? So we are asking something stronger in some sense. Yeah. And typically this subspace V is given to us as a matrix A, and we take V as the column space of matrix A. Yeah, thanks. So we want to preserve Euclidean norm of every vector of the form AX. Yeah. D relative to M. So think of it as like you need M to be at least D. So we want to get as close to D as possible. So any doubts here? So just remember this. We are given a subspace and we want to preserve norms of each vector in the subspace. That is Euclidean norm. Okay, so an application for you here. Say we have the general least squares regression problem. We are given n observations A1 through AN and corresponding values B1 through Bn. And you want to find a vector x that fits these observations well, the best in this particular error. That is, you want to find a vector x such that inner product between AIX minus BI squared is minimized over all the n observations you have here. And in matrix terms, if I'm calling this matrix as A and this vector as x, you want to minimize the Euclidean norm of AX minus B over all x's. And another way of looking at the problem is just that you are given this matrix A and you have these D columns. You want to find one value for each of the columns such that A times x minus B squared Euclidean norm is minimized. So note that for any particular x you are given, AX minus B lies in the column space of A appended with a column B. So yeah, this is just AX minus B. I wrote it up in terms of its columns. So for any given x, this particular vector lies in the span of A1 through AD and B. So suppose F is a subspace embedding for this particular subspace, that is column space of A adjoined with B. Then for all vectors x, we will have this guarantee, right? F times AX minus B will be within 1 plus minus epsilon AX minus B's Euclidean norm for any x. Now, if I am solving least squares regression problem just on the matrix FA and vector FB and get a solution x, that would be a 1 plus epsilon approximation for my original problem. But the thing is, now FA is much smaller than the original matrix A that I have started with. So I can hopefully solve it much faster now. Right? So to be able to take advantage of FA being much smaller, what are all the properties we desire of this embedding F? We want this F to be easily computable, right? If F is some weird matrix which takes very long to compute, where would you even apply that particular F and solve a downstream problem faster? So you want F to be as easy as possible to compute. And you also have to be able to apply F to a matrix A as fast as you can, right? Because in the earlier problem, we want to solve least squares regression problem on FA and FB. If applying F to A is much smaller, much slower than just solving least squares problem on A itself, then it won't be of any use to you. So this, yeah, sorry, I can just repeat it again. So this is the definition of subspace embedding. You are given a d-dimensional subspace in R to the n. You want to find a particular function which takes every vector in the d-dimensional subspace V to R to the m. Hopefully, m is much, much smaller than the original dimension n you started with. And the property you want to preserve is that you consider Euclidean norm of the original vector x, and you consider the Euclidean norm of the embedded vector E of x. You want Euclidean norm of embedded vector to be close to the Euclidean norm of original vector for all vectors in the subspace V. And for this talk, we only consider linear subspace embeddings, that is E of x is f times x for every vector x. Is it clear?
Yeah.
Yeah. Yeah. And F should also have very few rows, right? If F itself has a large number of rows, then we are not solving any smaller problem. So these are the three desired properties of a subspace embedding we want. That is, F itself must be easy to compute. F should be easily applicable to any given matrix A, and F should have very few rows. And this is our result. So given an arbitrary matrix A, there is a distribution S over M times N matrices. Here M is like D times poly log D, such that given any arbitrary matrix A, this distribution is independent of the matrix you want to apply it to. Okay, distribution is first, and for any given a sample from this distribution works with probability 9/10, such that for all vectors x, Euclidean norm of SAX is between Euclidean norm of AX and exponential in poly log D times Euclidean norm of AX. So here the distortion is not 1 plus epsilon as I alluded to earlier, but it is exponential in poly log D, which is asymptotically smaller than D, just to keep in mind. And a sample from this particular distribution S can be applied to a given matrix A in time, number of non-zero entries of A, and D squared term. Okay. So NNZA just denotes the number of non-zero entries in the matrix A, and our embedding works in input sparsity dimensions. So if you are considering sparse matrices, you don't have to spend n times D time, just the number of non-zero entries in that matrix A time.
Is it easy to check if a particular sample satisfies this?
No. What we say is a particular sample. I mean, you can, once you sample the matrix S, you can see the number of non-zero entries in that matrix S, and you can say, but before, so that particular sampling matrix S is sparse with a given probability, and then you can apply it fast to the matrix A.
But when you say poly log D,
Yeah.
what's the degree of that polynomial?
It's like maybe 4, I guess.
That's more useful than saying poly.
Yeah. Yeah, it's just hard to carry over the exact exponent, so I just put in poly there. Yeah. Yeah, so what's all the fuss with subspace embeddings? How can we even construct these? So one simple subspace embedding construction is as follows. You are given a matrix A, which you want to embed. Now consider an orthonormal basis for that matrix A. That is, Q just has orthonormal columns, and Q's columns span the subspace spanned by A's columns, right? And AX is an arbitrary vector in the column space of A. Then QQ transpose AX is exactly equal to AX, right? QQ transpose AX is just written, I mean, Q transpose AX is just the coefficients of the vector AX in Q's basis. And you are again multiplying Q with Q transpose AX, which just gives out the same vector. So for any X, QQ transpose AX is exactly equal to AX. And as I said, Q's columns are orthonormal. So by Pythagorean theorem, for any vector y, Euclidean norm of Qy is equal to Euclidean norm of y. So these are the two properties we have for Q. Now consider this Q transpose Ax plus Euclidean norm. By this property of orthonormality of Q, we have this is equal to QQ transpose Ax's Euclidean norm, which is exactly Euclidean norm of Ax. So what we have is this matrix Q transpose is a perfect subspace embedding for the subspace of A, I mean column space of A. But what properties does this even have? Like, we wanted F itself to be easily computable, but computing Q is very slow given a particular matrix A. So we don't have this. Should be able to compute FA quickly. Even if I am given Q in some manner, computing this matrix Q transpose A is slow because these are two dense matrices which we don't want to multiply. We also asked F to have very few rows. This is one particular property that Q transpose excels at. Q transpose just has D rows, where D is the number of columns in our original matrix A, and this is the least we can go. So this is optimal in terms of number of rows, but it doesn't have the other two properties we want.
That only makes sense when A is low rank, right?
Yeah. So think of D as being much smaller than N. Yeah.
Okay.
So the second attempt, we started with the idea that we want to preserve norms of every vector in a d-dimensional subspace. This seems to be a lot of vectors that we want to preserve, right? But a net argument says that for any subspace, you can find a set of like 2 to the order d vectors, such that if an embedding is preserving norms of just 2 to the order d vectors, it would preserve norms of every vector in the subspace, right? So we have reduced our problem of preserving norms of all vectors in the subspace to just try to preserve norms of 2 to the order d vectors. I mean, this is not a small number, but not infinite, right? And we have this JL lemma, which is famous, that you are given, so if G is a Gaussian matrix, that is each entry of G is independently and identically chosen from a Gaussian distribution. And if M is like epsilon to the -2 log 1 over delta, then for any arbitrary X, you can preserve its norm up to 1 plus minus epsilon factor with probability 1 minus delta. See the success relation between the success probability and M you need. To succeed with 1 minus delta, you only need order log 1 over delta rows in the Gaussian matrix M, right? And we want to succeed for like 2 to the order d vectors. So if I choose my failure probability to be like 2 to the minus order d, like 1 minus 2 to the minus order d, and if I pick my M to be like log 2 to the order d by epsilon squared, that is order d over epsilon squared, then this Gaussian matrix succeeds simultaneously for all the net vectors, right? I don't know what these net vectors are, but JL lemma says that for any arbitrary vector, this Gaussian matrix works. And if I choose my failure probability to be small enough, then it works for all the net vectors simultaneously, which gives me a subspace embedding. So if you are considering a dense Gaussian matrix with just d or epsilon squared rows, then it is a subspace embedding for an arbitrary d-dimensional subspace. Any doubts here? Yeah. So what properties does this Gaussian matrix have? First of all, it is easy to compute. You don't even have to look at the matrix A which you are applying it to. You just sample a Gaussian matrix. Should be able to compute FA quickly, but this is not possible. Like G is a very dense Gaussian matrix, and you want to multiply it with a matrix A. So it will at least take like number of non-zero entries in A times the number of rows in this Gaussian matrix. That is d over epsilon squared, which is lower than what we desire. And should have few rows. Yeah, at least for constant epsilon, Gaussian has like ordered, this is nice. And most important property I want to stress is that it is oblivious. This Gaussian matrix doesn't depend on the matrix A, which you want to apply it to. You can just sample it independently of the matrix A. So people try to fix these problems of Gaussians. One of the issues is we cannot apply it to the matrix A quickly because G is very unstructured, right? Each entry of G is independently sampled and it is very dense. So it's hard to apply to a given matrix A. So people proposed other constructions of subspace embeddings. First one is a subsample randomized Hadamard transform. I don't want to get into the details, but it has like d log d over epsilon squared rows. It is worse than Gaussian by a factor of log d, but it can be applied to a matrix quickly. Say you have an n by d matrix, you can apply this in n d log n time. The second one is count sketch, which has even more rows, d squared over epsilon squared rows, but it can be applied very quickly just in the number of non-zero entries in matrix A time. And third one is a family of constructions called OSNAP. Here it is parameterized by this gamma. You can take gamma to be anything and get a number of rows like d to the 1 plus gamma log d or epsilon squared. But the time to apply it is 1 over gamma epsilon times NNGA. So take gamma as say 0.1. You will get an embedding with d to the 1.1 log d over epsilon squared rows. And it can be applied in NNGA over epsilon time. And the final one is leverage score sampling. This is non-oblivious in the sense that you need to look at the matrix A to construct leverage score sample, but it has d log d over epsilon squared rows, and it can be applied quickly too. This polynomial is like d to the 4. Yeah.
So are all these numbers for both of these like worst case or like average case, or is it the same?
No, it is the same. Like they will take this amount of time. These are all deterministic time.
They
Yeah.
always take that.
Yeah, exactly. Yeah. So what we can see is none of these have the good property of Gaussians, right? For Gaussians, for constant epsilon, we only needed like, but all of these are like d log d rows. But the advantage here is that we can compose the subspace embeddings. I can first apply a count sketch matrix, then compose it with a Gaussian. It would still be a subspace embedding because my constructions are oblivious to the matrix I'm applying it to, right? So I can go from n rows in the beginning. If I first apply OSNAP with a gamma parameter, I can get down to d to the 1 plus gamma log d rows, considering constant epsilon. And I can again apply an OSNAP embedding with gamma equals 1 over log d, which gives me d log d rows. Now I can apply a Gaussian to get to d rows. So I can chain these subspace embeddings in any manner I want, and they all work because they are oblivious. So going from original matrix to d to the 1 plus gamma log d takes me gamma inverse NNGA time. Think of gamma being a small constant here, like 0.1. And I can go from d to the 1 plus gamma log d to d log d in order d to the 2 plus gamma log square d. This gamma is just the same as original gamma. No? And I can go from d log d to d by just multiplying with a dense Gaussian matrix, which will take d to the omega log d. Here d to the omega is just the time required to multiply two d cross d matrices fastest. Okay, so what we now have is in time like NNGA plus d to the say 2.1 plus some little o of 1 plus d to the omega log d time, you can get to d rows for a subspace embedding. But you want to do faster than d to the omega log d. For many problems, d to the omega is like the fastest time you can perform it. And we want to eliminate this log d factor for many of the problems. So we want the construction of subspace embedding to take lesser than d to the omega time. Any questions here? So our main aim is to construct a subspace embedding that runs in like NNGA time plus d to the some exponent where that exponent is less than gamma. Sorry, omega. Okay, so this is what we are trying to focus now. We want to construct a random matrix S that is a distribution such that each matrix. Sorry?
So you're not really caring about what epsilon is?
Yeah. So think about epsilon as just being a constant. So we want to construct a distribution such that each matrix from the distribution has little of d log d rows. And for any matrix A, we want it to be able to be applied in like NNZ A plus d to the C for some C, which is less than matrix multiplication exponent. Currently, it's like 2.3, omega is like 0.3. So we are fine with anything less than 2.3. And with probability 9/10, it has to be a subspace embedding with alpha that is as small as we can get, right? Distortion alpha. So what do we do? Like all the subspace embeddings I described about has d log d rows except the Gaussians. So we just go back to Gaussians and try how we can improve the Gaussian embedding itself. The problem with Gaussians was multiplying it with a matrix was hard, especially because the Gaussian was a dense matrix without any structure. So we tried to look at how sparse we can make this Gaussian matrix. If each row of the Gaussian matrix has very few non-zero entries, then we can multiply it with a matrix very quickly, right? So our entire algorithm is about making G as sparse as we can while still preserving the subspace embedding property. So what we observed was that for some very special subspaces, we can make G very, very sparse. And as I said, sparse matrix, if G is very sparse, you can multiply it quickly. Now without loss of generality, we assume that our matrix is a d log d over d matrix, just using this conversion I said, but we just stop here at d log d rows, right? Which can be done in gamma inverse NNZA time plus d to the 2 plus gamma log d. And picking gamma as like say 0.1, we are doing better than the current matrix multiplication time. So from here on, we assume that the matrix we want to embed is a d log d over d matrix. Okay, so what's the idea here? So suppose S is just sampling some coordinates of the vector x, and you want to make S to preserve the Euclidean norm of the vector x. And say if x is just a coordinate vector, that is just it has 1 in one coordinate and 0 elsewhere. And if your S is sampling d coordinates of this vector x with very high probability, that is with 1 minus 1 over log d probability, you would miss this non-zero coordinate, right? You have a d log d vector with just one non-zero coordinate, and you are sampling d random elements of this vector. With probability 1 minus 1 over log d, you will be missing this non-zero coordinate. So sampling d coordinates wouldn't work if x is just a coordinate vector. On the other extreme, think of x as being 1 over square root d log d in each coordinate. You have d log d coordinates, and it is 1 over square root d log d in each of the coordinates. And now sampling d coordinates would let you estimate the Euclidean norm well, right? With probability 1, you will have the sampled coordinates Euclidean norm as very large, that is 1 over square root log d. So we have two sorts of extremes where if x is a very sparse vector, sampling doesn't work well. But if x is very dense vector, sampling works well in estimating its norm. So this is the property we want to make use, that if a subspace, if each unit vector in the subspace has a large number of large coordinates, then sampling is easy. That is what we want to prove. And so essentially, a vector is nicely sketchable with sparse matrices if its L1 norm is very large. So consider a unit vector in R to the d log d. If its L1 norm is say like square root d, that is just the sum of absolute values of its coordinates is large, then it is easily sketchable by sampling few coordinates. This is the intuition behind our idea. So now we want to give a distribution of matrices such that mx is greater than some fixed value with very high probability, given a vector x satisfying the property that its L1 norm is large, right? So we consider an arbitrary unit vector x such that it has this property. That is, it has at least a constant fraction of d times coordinates with value at least 1 over square root d, right? So these are like large coordinates. We have CD coordinates, each with value at least 1 over square root d. So these capture a large fraction of L2 norm of the vector x. Now consider any vector x that has this property. Our embedding is very simple. With probability 1 minus p, you set entry of the matrix 0. With probability p by 2, you set it as +1, and with probability p by 2, you set it as -1 for very small probability p. So most of the entries of this matrix are zeros. Yeah.
A question in chat. Why are we dimension d log d? Are you hitting the original vector with some other subspace embedding?
Yeah. So as in this conversion, we can go from n r to the n to r to the d log d by just spending gamma inverse n and z time plus order d to the 2 plus gamma log square d for a small constant gamma, which is better than n and z plus d to the omega already. So we are assuming that we want to just embed d log d subspaces in dimension d log d. Yeah. Yeah. So the random matrix we are constructing here is simple, as I said. With very high probability, you just set it to 0. And with the remaining tiny probability, you set it to ±1 with equal probabilities. And we want to show that it doesn't contract the Euclidean norm of vectors such as which have this property. That is, with very large probability, its Euclidean norm is large. So this O tilde one just hides the logarithmic factors in D. You want it to be large, essentially. And the probability of setting it to be non-zero is only like theta 1 over d. Now we have constructed this particular matrix M by just sampling non-zero coordinates of this matrix M, right? This is set to 0, this is set to 0, this may be +1 and 0. A large number of entries of this matrix are zeros. This is what you have to care about. And rest of the entries are ±1 with equal probability. Now I am considering a fixed unit vector x. What is the probability that I have a non-zero coordinate in one of the large coordinates x? So just look at the first row of this matrix M. And I have CD large coordinates in the vector x. Now what is the probability that the first row of this matrix M has a non-zero number in one of the coordinates where x is large? It is constant, right? With at least a constant probability, one of the coordinates where x is large, M will have a non-zero coordinate. Because I am setting it to be non-zero with probability theta 1 over d, and I have CD non-zero positions. So with at least a constant probability, I'll have a non-zero entry in one of the large coordinates of x. And suppose M1, the first row of M hits the vector x, that is, has a non-zero coordinate at one of the large positions. How large would the contribution of M1 x squared will be? So we consider the aside now. So what I'm even trying to do, I want to show that mx squared's Euclidean norm is large, which is just the sum over all the rows of mi star x squared. And I want to show that with good probability, each of these contributions would be large. And now I'm just considering the contribution of first row, assuming that the first row hits the large coordinates of x. So now consider a random sum. You are just given n values, x1 through xn. These are fixed values. And you are also given that the absolute value of xn is the largest, right? And you are multiplying each value with a random sign, that is plus minus 1 with half probability each, and just adding them up. And we want to see how large this absolute value would be. That is absolute value of r1x1 through rnxn. Now fix a value for rn, say plus 1, okay? And consider the remaining partial sum, that is r1x1 through rn minus 1 xn minus 1. Now this is independent of the sign of rn, right? Because each of them are chosen independent of each other. So with half probability, the partial sum r1x1 through rn minus 1 xn minus 1 will have the same sign as rn xn, right? So if I just add up the whole thing and take an absolute value with half probability, r1x1 through rn xn will have an absolute value of at least rn times xn's absolute value, which is at least xn. So what it all says is that if you are given n elements and multiplying each of them with random signs and adding them up, the absolute value you get is at least the absolute value of maximum element you are adding with half probability, right? So basically, if first row hits one of the large coordinates of x, m1 star x would be at least equal to the largest coordinate that it hits with probability half. And so the first event of hitting happens with constant probability. And again, once you are given that it hits with half probability, you will capture a large value. So with constant probability, m1 star x squared, that is contribution of just the first row, would be at least 1 over d. Because it hits a coordinate of magnitude 1 over square root d. So what we currently have is that a row with constant probability contributes 1 over d to mx squared. Yeah. So each row is independently large with a constant probability. And just using matrix Chernoff, we know that there will be large number of large rows. That is at least CD. If I am considering M to be CD, that is the number of rows of this matrix M to be some constant times D. And each row is independently large with a constant probability. So I will have like theta D rows, which are large, right? And each large row contributes 1 over d to the mx squared. So with very high probability, mx squared will be at least theta 1, hiding logarithmic factors. Okay. So you can give me any vector x that has a large number of large coordinates as defined. Then with very high probability, that is 1 minus exponential in minus theta d, this is very small failure probability. Mx squared would be large. Yeah, for a unit vector that satisfies the guarantee. And we showed one side of our guarantee that is required. That is mx squared must not be too small for a unit vector. And turns out the other side, that mx squared is not too large, is pretty easy to show. Just because m is very sparse, it is kind of easy to show that it doesn't blow up the operator norm, the Euclidean norm of any vector x that it is applied to. Yeah. So what did we learn? If you are given a unit vector which has a large L1 norm, that is if its sum of coordinates is very large, which is given by the fact that it has a large number of large coordinates, then this matrix M works well as an embedding. And if the entire subspace, if unit vectors in the entire subspace have this property, then this M is a good subspace embedding. But of course, the subspace we have may not have this property, right? We are given some arbitrary subspace in R to the d log d, which may not have this subspace. So we want to transform any given subspace to a subspace that has this property. For this, we use a transformation from an old paper of Endick, for which we prove new properties and show that it takes any vector, any given vector x this transformation spits out a new vector x that has the property we desire. So this is the new result that we show for index embedding. Let me go over this. You are given an arbitrary n and consider m to be n to the 1 plus little of 1. So you are given an arbitrary vector x in n dimensions. The transformation spits out a new vector in m dimensions, which is not too large. I mean, just n to the 1 plus little of n, 1. Think of it as n log n or so. And you are also given a partition of this m. So the new vector is divided into equal sized parts around square root n parts. Okay. Then index embedding gives the following result. There is a mapping f that takes vectors from r to the n and gives vectors in r to the m, and a partitioning of the m coordinates such that for any vector x, this embedding can be computed quickly. That is n to the 1 plus little of 1. Think of it as n log n. For any vector x, Euclidean norm of fx squared is like 1 over b times Euclidean norm of x squared. So you start with a unit vector, then squared Euclidean norm of fx would be like 1 over square root n times 1. And for any vector x, as I said, you divide this fx into square root n equal sized buckets. If you add up Euclidean norms of each bucket, then it will be close to Euclidean norm of the vector you begin with. So say you started with unit vector x, then if you add up Euclidean norms of these buckets, you will get close to 1. So I have a picture to make it clear. You start with a vector x, f maps it to a larger vector fx, which is divided into b buckets. And now x is mapped to say this large vector with y1 through yb. Each bucket corresponds to a vector yb. Then if you add up squared norms of these yi's, you will get 1 over b times squared norm of x. And if you add up just Euclidean norms of these buckets, you will get the Euclidean norm of original vector. Right. So what we essentially do is we start with this vector x, apply f to this to get a larger vector x, fx. And for each bucket, we recursively apply this transformation again. So for y1, we will apply f, y2, we will apply f, for yb, we will apply f, and we recursively apply this for theta log n levels. And at the end, the vector we obtain, I'm denoting it with a curly fx, has this property that it's one norm, that is just the sum of absolute values of coordinates of curly f times x, is at least square root n by 4. It's pretty large. I mean, you start with an n-dimensional vector and you end up with like n log n type vector, such that its Euclidean norm is large, whereas its its L1 norm is large, but its squared Euclidean norm is still between half and 1. So if you start with a unit vector, you will get a vector whose squared norm is like between half and 1, but its L1 norm is very large, like square root n. That means this curly f times x will have a large number of large coordinates. That is, it will have like a constant fraction of n times coordinates that are at least 1 over to the little of 1. Yeah. If it is a unit vector. So this result is not as good as the one we hoped. We were like trying to get 1 over square root n contribution, right? But even this 1 over n to the little of 1 suffices in giving our subspace embedding results. Yeah.
You mean 1 over n to the power half?
Yeah, sorry. And 1 over n to the half plus little of 1. So we started with trying to get an embedding which takes a unit vector x and maps it to a new vector fx, such that it will have at least cn coordinates having a value of 1 over square root n. but this transformation only gives like 1 over n to the half plus late law of 1. So basically what we are saying is you can transform any given subspace into a subspace where every unit vector has a large number of large coordinates. And as we saw earlier, for this kind of subspaces, very sparse sign matrices act as subspace embeddings. So you start with a given matrix A, you take it to a d log d by d matrix M, sorry, B. And now we can apply this matrix M to get a new matrix M times B. This M will have like d poly log log d rows and is a subspace embedding for the original matrix A. Any questions here or clarifications? So I'll just take you back to the main result and we can just go over again. Yeah, this is the final result. That is, we give a distribution over matrices S with d poly log log d rows. Think of it as d times log log d to the 4. Yeah.
So you apply OS and OS and AP and then flattening lemma and then you concept.
Yeah. So the final result is you start with an arbitrary n by d matrix. We can apply a random matrix which has like d times poly log log d rows, such that for given any arbitrary matrix A, for all vectors x, you preserve the Euclidean norm of x. So SAX is between Euclidean norm of x and distorted by at most exponential in poly log log d factor, which in general suffices to get fast algorithms. And using the new transform, we improve running times for many problems. I mean, not many, 4 problems. So using our construction, we give fast construction of epsilon subspace embeddings. As I said, our distortion is not good. It is exponential in poly log log d, but it can still be used to construct fast 1 plus epsilon subspace embeddings in this running time. So the main factor you have to focus on is this dependence on d. The new dependence on d is just d to the omega poly log log d instead of log d we saw earlier. So we made a contribution in removing this log factor, which has remained for many years essentially. And we also solve epsilon approximate linear regression. So you want to, given an instance of linear regression, you want to obtain a 1 plus epsilon approximation. And this also has a d to the omega poly log log d dependence now. And we also give an algorithm to compute linearly independent rows. So you are given a matrix A of rank K, and you want to find K linearly independent rows of this matrix A. You can now do it in like input sparsity time plus just the K to the omega poly log log K factor. So if K is the number of linearly independent rows you want to find, you will spend K to the omega poly log log K time. And this was also earlier K to the omega poly log K and NNZA times poly log K. So we removed log factors from this running time too. And we also give fast algorithms for rank K approximation in Frobenius norm. Now the algorithm just runs in input sparsity and n plus d times K to the omega minus 1. So if you want to find like lower rank K approximation, you only spend like K to the omega minus 1 times n plus d time. Here also we removed a log factor from earlier algorithms. So our main contribution is removing the log factors from the previous algorithms, which have like been there for many years. So yeah, that's what I have. Thanks. Any questions?
Just maybe a relevant question, but does this have any practical, do you envision this
Yes.
in the practical applications to apply it, machine learning problems or?
Yes. So currently Gaussians and count sketches are pretty well used. So if you look at this table of subspace embeddings, these are quite used. So count sketch and randomized Hadamard transform are pretty used in practice. But our implementation uses this flattening transform of indic I mentioned, right? Which is like not implemented in practice. So I guess if one has like fast implementation of the embedding we were talking about, then this can very well be used in practice for fast algorithms. Yeah, so there are all the pieces are there except for the main transformation we are using.
Could this approach be adapted to LP subspace embeddings for other P, for example, by using sparse Gaussian matrices? If they're flattened, that would help.
Oh, I'm not sure about that. Yeah.
So Praneeth, can you hear me?
It's yeah, I mean, it depends on L2 to L1 constructions. We use an L2 to L1 type of construction here. So I guess L2 to LP type of constructions will help in that. Yeah.
So can this, so like in your theorem, you have like different conditions on like how much the length varies as well as like how fast it is. Could you like choose some like slight trade-off there? Like I want it to be slightly more precise, like 1 plus or minus epsilon, in exchange for letting it take a bit longer. Like can your
No. So our construction can only give like exponential in polylog log D distortion.
okay.
Yeah.
So it can't
It can't be directly adapted to
be
give.
adjusted like the other way, like give slightly more distortion and then slightly less time.
Yeah, I mean the intermediate things you would use can be worse now.
Okay.
Yeah.
Okay. So like just doing the steps, the iterative step, like a bit more time.
Yeah. Yeah.
Is the reason you need an index as opposed to a generic Euclidean section of L1 that index maps to be computed in linear time?
Yes, and the other sections won't have this property that they will make progress towards getting large number of large coordinates too, right? We need this property mainly that we want to transform any given unit vector into a new vector that has the property that it has a large number of large coordinates in the sense I mentioned. And of course, we also want near linear time construction.
Can you repeat why number of rows is like?
Yeah. So the motivation I started with was like, you want to solve linear regression and you apply this embedding F to both the matrix A and the vector B. If F itself has like large number of rows, then the new problem you are solving is not small. The new problem you are solving is F times A and F times B. To solve this fastly, you want FA to be small. That's why we want as few rows as possible.